All right, so let's get started. We have a theory speaker here, Flavio.
Chierichetti.
Huh?
Chierichetti. Chierichetti is okay. So.
Chierichetti. We have Flavio Chierichetti here from Cornell, and he did his PhD in Rome and is now a postdoc with John Kleinberg, and he'll be talking to us about some research he's been doing in voting.
Thank you, Nicole, and to everybody for having me here. So I'll be talking about this paper we had, voting with limited information and many alternatives. And since I can describe the main problem as a puzzle, I will start by doing that. So as in the title, it's a voting game. You have a bunch of urns. These are the candidates. And each urn contains, say, some number of blue and some number of red balls. Okay? And you have two competing parties. One is the adversary, and the other one is a set of voters, of people. So what will happen is, at the very beginning, the adversary will pick one urn without telling the voters. Okay? And then the voters basically have to guess which urn did the adversary pick. What the voters know is the original set of urns, the set from which the adversary picked one given urn. And then, they can do the following. So one after the other, they go to the unknown urn, and everyone gets to pick a single ball. So maybe, the first guy, the blue guy, picks a red ball, and he thinks of the urns, and he makes a guess on which urn actually produced this red ball. Remember that this urn was one of the urns right here. So, maybe he says, well, maybe it's the red one, since it had all red balls. And so he will write in his ballot that he believes that the right urn is the 100% red urn, this urn here on the right. Then, say the green guy comes, again he picks one ball, maybe he gets a blue one, and he will say, maybe I believe that it's the old blue urn. So we write 0% red and put his vote in the ballot. So observe that, voters cannot really just pick either the old blue one or the old red one. If the adversary picked one in the center, they would lose, as you can imagine. So if the yellow, if another guy, the yellow guy, picks a blue ball, maybe he should vote for the second urn, say the 20% red, 80% blue urn. Okay, so that's what the voters can do. One important thing is, of course, the rules of the game, which are the voters win if and only if the correct unknown urn gets largest number of votes. So that's when they win. And I guess the most important point is that voters cannot communicate with each other at all. And of course, at the very beginning, they can decide a strategy that they can use. But once a voter picks a ball, then he cannot say anything to any other voter. Okay? And everyone gets a single ball. So you can imagine that, if voters, if there was a single voter, then nothing can be done, right? You would pick either a blue or red ball, and there are many urns that would produce that blue or that red ball. So one of the corollaries of our result is that if you have, say, n plus 1 distinct urns, so basically a 0 blue balls urn and red, and then 1 n minus 1, 2 n minus 2, up to 0n, then there exists a strategy that allows n voters to win with probability at least 1 minus eta, if and only if the number of voters is at least n to the 5th log 1 over eta, and this is tight. So if you have this many voters, then you will win with probability 1 minus eta, and if you have fewer of them, then there's no strategy that would work.
Are you going to give motivation?
Yeah, in a slide. Next slide, I think. So why do we consider this problem? So this was introduced in the political science literature by Austin Smith and Banks, and they wanted to model jury voting. So you have, say, a defendant that's accused of having done something, say, of having killed a man, and there are many possibilities, right? Either the defendant is innocent, or guilty of manslaughter, or first-degree murder, or any other you can think of, and each of these possible statuses of the defendant is a different turn, right? We can imagine that an innocent defendant has many blue balls, blue meaning that there's an evidence that the guy is innocent, and red an evidence that the guy is actually, that actually committed something. And so for each different possible status, you do get a different distribution on the two colors, say the red and the blue color. Okay, and the reason why Austin, Smith, and Banks claimed that jurors couldn't communicate with each other is that when you listen to all the discussion of the process of the defense and of all the people in the process, you form a feeling in the back of your mind of whether the guy is innocent or not, and you cannot really communicate that feeling to other jurors, to your fellow jurors. You just have a feeling on the back of your head that the guy is innocent or not. And so what they asked was, assuming that the jurors really have the one goal of making the right decision, how should they coordinate to make the right decision, to either convict or not the guy, depending on whether he was guilty or not. So you can consider exactly the same problem in a different setting, which is, say, suppose you want to elect a sheriff for a town. Then which candidate should people vote for? Each candidate again is a different term. And what candidates do is they propose amount of money to be spent on crime fighting. So maybe there's a candidate that says, I want to spend 100K in a small town, and maybe there's another candidate that say, I want to spend 500K or something. So you know that, so you actually have a feeling of what these earns look like. And in the year before the election, you either saw or not a crime in your backyard. And based on that, you have to guess whether crime is really an issue in your town or not. So the two signals, the two colors you have here are you saw a crime or not, and again the earns are the different candidates, each proposing a different policy for crime fighting. And so we call this general type of say voting problem information-based voting. And the main point here is that voters are really trying to translate one language into the other. The first language is the language of colors. You see some type of signals. Did you see a crime or not? And you have to cast your observation in another language. Which candidate should I vote for? So each person here really wants to make the right decision. There's a best sheriff. If you knew exactly what's the crime rate in your city, you would know which sheriff to vote for, and everybody, would do the same. Thing is, every one of us has only a limited knowledge of what the crime rate in our city is, and what the voters are really trying to do is translating one signal, a color, into another signal, a candidate. And how can they do this? So the problem, again, as I told you, was introduced in the political science literature, and they didn't phrase it as I did, so as some sort of type of combinatorial problem. It was actually a game, and the voters were the players. And the thing is, in this game, every voter got the same payoff. So we all get $1 each if the correct earn wins the election, and $0 otherwise. So basically, every player really had the same goal, which was maximizing the probability that the right earn, the right candidate, won the election, and therefore, many of the issues you usually deal with when you study game theory disappear. In that, say, for instance, the price of stability is 1. If you find a set of strategies that maximizes the probability of winning, then if everybody sticks to those set of strategies, of course you get an equilibrium. What we prove is that if you have this many voters, that's the result I told you about at the very beginning. If you have this many voters, then there exists an equilibrium where each player gets almost the maximum possible payoff, 1 minus 0, and of course the maximum you can get is $1. And again, very easily, there exists an equilibrium where each player gets a payoff of 0. And suppose whenever we claim that whenever we're going to pick a red ball, we will be voting for the all blue earn, and whenever we pick a blue ball, I will be voting for the all red earn. This means that no matter what happens, we will the wrong earn will win, right? So there exists an equilibrium where the social welfare is 0, and therefore the price of anarchy is infinite. Okay, so these are just some game theoretical aspects of this process.
Why is that bottom example in equilibrium?
Oh, okay. Suppose that basically everybody announces that it will be doing that, and suppose you want to change, right? You say, okay, this is a very bad idea, so I will do something different. Thing is that the majority.
Okay, just so yeah.
Right.
So it's not really an equilibrium in a strong sense that I want to do this. It's just that I can't affect the outcome.
Oh, yeah, exactly. Yeah, exactly. So you need at least alpha times n many people to change their strategy for changing the outcome.
Okay.
So it's also a very strong notion of equilibrium, right? You need to change, basically n over too many people strategies. Yeah. So I'm going to, so the first thing, I was spending a lot of time talking about this result, and so that's what I'm going to do right now. So instead of telling you about that result, that n over fifth result for equally spaced urns, I'm going to tell you something different, something more general, which is suppose now that say the distribution of red and blue in the urns is not equally spaced. So you have n urns, each of which has some red fraction of red balls. The red fractions are all different, for otherwise, there's no way you could win with that probability. And say, the red fraction of the first urn is at least 0, and it's P1, which is less than P2, the red fraction of the second urn, up to Pn. Okay? Now, of course, suppose that, I give you even just 2 urns for which the red fractions are very, very close to each other. And I make them, say, 1/2 plus epsilon and 1/2 minus epsilon. Then, of course, the number of signals or voters that you will have to have is going to grow as epsilon shrinks to 0, right? So we define this epsilon, which is the minimum over I of the difference of the red fraction between 2 neighboring urns. And this epsilon, you can see that it's just a constant factor times the minimum L1 distance between 2 different urns distribution. And what we will be showing is that if you have n cubed over epsilon squared times some logarithmic term, many voters, you have enough voters to win with probability at least 1 minus 0. Right? And observe that if n is a constant, as in, say, the jury case, then you only need epsilon to the minus 2, which is tight in the sense that even if you have a centralized algorithm that gets to pick epsilon to the minus 2 many balls, well, that's the minimum number of balls that a centralized algorithm will need to take for guessing which one was the right one. So if n is a constant, this is tied to the optimal centralized strategy. And I will be telling you something about why this is also a lower bound in the voting case, but I won't have time to tell you about all the details of the proof. So let's think about what a strategy is. Suppose I'm the green guy, and suppose I announce a strategy. Then what am I really doing? I'm saying that if I pick a red ball, then I will be choosing one of the urns according to some probability distribution, R0, R1, up to Rn. And if I pick a blue ball, then I will be choosing the urn to vote for according to distribution B0, B1, Bn. That's really what am I going to do as a player, as the green player. And each player might have, of course, a different couples of distributions. Say the yellow guy could have R prime 0 up to R prime n, and B prime 0 up to B prime n. So let's try to start to analyze what different strategies that we saw are really just couples of probability distribution, how different strategies help or do not help the right urn to win. Okay, so recall that Pi is the fraction of red balls in urn I, and take one player, say the green one, that has strategy R0 Rn and B0 Bn. Then what's the probability that this player, using this strategy, will be voting for urn J if the unknown urn is I? Okay, that's easy to compute. It's just the probability that he picks a red ball, Pi. Pi is the red fraction of urn I of the unknown urn, times the probability that he will be voting for urn J if he picks a red ball. Plus, of course, the probability of picking a blue ball times the probability of voting for urn J if you pick a blue ball. So that's Bij is just the expected number of votes that a player will be giving to urn J if the unknown urn is I. And observe that, of course, if I change the unknown urn, if I change the Pi, then this probability, this expectation will change, of course, right? Because Rj and Bj will be different in general. So we want the right urn to win, right? And to do that, at the very least, we want that on expectation, the right urn will win, meaning that the expected number of votes to earn I, if the unknown urn is I, has to be much larger than the expected number of votes to earn J if I is the unknown urn. And this has to hold for each I and J, right? Because
the question when you're, how the voters take the ball, is it with replacement?
It's with replacement, yeah. So it's basically you have distributions and everybody picks a random sample from the same distribution. Yeah. Right. And so you want this to hold for each I and J because the adversary picks the unknown urn. So if there's an I for which this doesn't hold, the adversary will win, and therefore the voters will lose with high probability. And also it has to hold for each J because, well, you want really the high turn to get the largest amount of votes, which means that every other urn has to take less votes than I. So since we want this to happen, let us define delta ij to be the expected number of votes to earn I if I is the unknown urn minus the expected number of votes to earn j if I is the unknown urn. And what we want is delta ij to be as large as possible, definitely positive, but as large as possible for each I and j. So if you do some computations, you end up with this linear program. So as I said, you want delta ij to be as large as possible. Delta ij is just the expected number of votes to I versus j. The ij is what we observed. So the expected number of votes to earn j if I is the unknown urn. And we want delta ij, so the smallest delta ij, to be as large as possible because the adversary is going really to pick the urn that makes delta ij the smallest possible. So we want to maximize delta, which has to be smallest than every delta ij, under the condition that the sum of the RIs, so basically the strategy for the red ball of the player is a probability distribution, so the sum of the RIs is 1. They all have to be non-negative, and the same has to happen for the PIs. So in this linear program, of course, the PIs are known, they are just constants. You can imagine they're constants, and Ri and PIs are the unknown variables. Okay? And so the question is, how big can you make this delta, right? If you can make it positive, if the best solution has a positive delta, this means that you will win after a while, right? Because, well, you get, say, a positive edge, an expectation. So, by the central limit theorem, if you go on for enough many voters, you will win. If you get delta equals 0, and observe that getting delta equals 0 is trivial, what if every voter just votes uniformly at random, regardless of the ball he picked, right? Then, this expectation will always be the same. It will always be 1 over n, regardless of I and j. So delta will be 0. And so the maximum small delta will be 0. So the question is, can we make this positive? And by how much, right? You can imagine that the larger this gap is, the better we are. And in some sense, this is true. And again, so the variables here are the RJs and the BJs. Okay, so one thing we do, and I won't be telling you really how we do it, because it's complicated, but it's not maybe the most interesting thing here, is that the best delta, so the optimal solution of this linear program is at least epsilon over n squared. Recall that epsilon was the minimum L1 distance between two urns distribution, and n was the number of urns. So we can show that there's a positive delta, and in fact, it gets this I. Well, or you could say it's only 1 over n cubed if they're equally spaced, but that's really the best you can do. And more specifically, we give a solution such that the expected number of votes to urn I for each unknown urn I is roughly 1 over n-ish. So the right urn will get, maybe 2 over n, 3 over n, many votes on expectation. So it will be, say, the first one, the best one, but it will only win by a very tiny amount. And in fact, delta ij, the gap that the high urn has against any other j urn, only grows like epsilon over n squared times, the absolute difference between the indices psi and j. Okay. And so, well, if you take j equal I plus 1, then you get a tight bound for epsilon over n squared.
What's that epsilon value? Is that the difference between the two indices, I minus j?
I minus j, yeah, exactly. So basically, so recall that the urns are sorted according to the red probabilities, right? Yeah. And in fact, you could remove epsilon times I minus j in absolute value and just write down pi minus pj in absolute value, okay? But it would be more convenient to have this. Yeah. So one thing to be said is that I lied. And actually, we don't really show this because this is not true in general. And this is true if the urns probabilities are symmetric around 1/2. So say in the equally spaced case where you basically put probabilities between 0 and n equally spaced, between 0 and 1 equally spaced, then this is true. And in general, if it's the case that if you have a urn with probability p, then you also have a urn which has the symmetric probability around 1/2, which now I don't want to do a computation because it will be wrong. But so if you have 1/2 here, then if you have a p here, you also want a urn distribution, an opposite distribution around 1/2 here. And if that is true, then this holds. In general, this doesn't hold, so we have a more complicated lower bound here. But basically everything that I will be telling you works even in this more complicated case. So I will just let it slip under the rug. Okay. So again, I said that we give a solution to the linear program, but the solution is actually an algorithm or a strategy for the players, right? So suppose that the solution is R0 star, Rn star, and B0 star, Bn star. Then what I'm saying is that the players will play a symmetric strategy, which is if they pick a red ball, then they will vote according to this probability. Every of them will do the same. If they pick a blue ball, then they will vote according to the second probability distribution. So voters are symmetric. Yeah. And so why do these bounds help us? Well, suppose you have, say, alpha n cube over epsilon square many voters. Recall that we proved that roughly n cube over epsilon square is the right amount of voters we need. So what happens? Let me use xj to denote the total number of votes given to urn j if the unknown urn is I. Okay? Just the total. So what's the expectation of the difference between the number of votes to urn I and urn j? Well, we know that delta ij is at least epsilon over n squared times I minus j, which is this thing here, multiplied by the number of voters. And the reason why I can multiply is that's an expectation, and every voter is applying the same strategy. So, this difference is just the sum of these bounds over all the voters, and we have this many voters. So if you do the math, you end up with a lower bound, which is alpha times n over epsilon. And again, you should imagine alpha as being a constant, a large enough constant. So that's the expectation. So that's, I guess, the expected edge we get over any wrong urn. What about the variance, right? That's an important thing, because even if, say, my expectation was positive 1, then it doesn't mean that I will be winning, because maybe, one of the wrong urns, there are many of them, will actually beat the right one. Even if on expectation, the right one would win. So first of all, observe that the variance, the standard deviation of the number of votes to a wrong urn is upper bounded by the standard deviation of the number of votes to the right urn. And the reason is, these are really Bernoulli trials, and by saying you that delta ij is always positive, I'm really telling you that it's more likely that you will be voting for urn I as opposed to urn j. So that's kind of the reason why you get this upper bound. And so let's compute it. Well, this is just the square root of the number of voters, alpha n cube over epsilon squared, times the probability that you will be voting for urn I, times 1 minus that probability, but since it's so close to 1, we kind of disregard it. This probability, as we showed in our solution, is 1 over n-ish, so we get alpha n squared over epsilon squared with a square root, so we get square root of alpha times n over epsilon, right? And so you can see here that the expected gap is larger than the standard deviation of the two variables that make up this gap. So if you want a picture, suppose this is the number of votes, okay, from 0 to infinity. This is the expected number of votes to the right urn I, which is bigger than the expected number of votes to urn j, for any j different from I. And this blue line, the gap between the two, will be at least alpha times n over epsilon. And the standard deviation would be smaller. if you make alpha grow bigger and bigger, the standard deviation will grow like square root of alpha times n over epsilon. So, say pick alpha equal 10 or 20, then you get that the blue line will be larger than the red lines. And therefore, with some reasonably high probability, xi will end up in this interval here, xj will end up in this interval here, and this interval is disjoint because alpha is bigger than square root of alpha. So that's really the reason why it works. And in fact, you can, that's really the heart of the argument, plus, of course, the solution of the linear program. That's, I guess, even more important. But, once you have this, you can easily, apply Chernoff bound to show that it's not just that I will win against a given Urn J, but actually you can get, a win against every other Urn. And so that's why n cubed over epsilon squared times log 1 over eta many voters are enough to get a probability of 1 minus 0. Okay. Right. So one thing that that sometimes people ask is why can you why don't you have, say, a log n factor here, right? You're actually, here you're competing only against j, but then you have n minus 1 many possible j's. So why don't you have to have, some sort of union bound argument? And the reason is, look, so I consider this lower bound, alpha times n over epsilon, but actually the lower bound was alpha n over epsilon times the absolute difference between I and j, which means that, say, if the right term is I, then I plus 1 and I minus 1 roughly have, are kind of close in expectation, turn Urn I, but as long as you go from, say, to I plus 2, I minus 2, I plus 3, I minus 3, the expected distance will increase, right, linearly. And therefore, it's really, you can only lose two Urns that are closest to you. The ones that are far from you don't really matter. That's why you don't need the extra log n factor. So the solution of this linear program, again, was the heart of the voters algorithm. And in fact, it was really just the voters algorithm. Now, I didn't show you that solution because it's complicated, quote unquote, a rational function of the PIs. And so one natural question is, do simple solutions work, right? Something that you can easily explain. So so I say complicated, it's not really too complicated, but it's, really a sum of rational terms, of, basically fractional terms. So if you're interested, you can look at it in the paper. But I want to try to tell you what happens with simple solutions, so reasonably looking solutions. So one thing that people suggested is, why don't players just use base rule? And by base rule, I mean the following. So assume that we really don't have an adversary, and actually let us change the game, and let's say that the unknown Urn is chosen uniformly at random. Okay, so we pick the unknown Urn uniformly at random, and then a player votes according to the likelihood that Urn I was chosen. Okay, based on whether he picked the red or the blue ball. Okay, so this means that if I pick a red ball, then the probability that I will be voting for Urn I is just pi, the fraction of red balls in Urn I, over the sum of the red probabilities of all the Urns. And if I pick a blue ball, I will do the opposite. So it's just the probability that a blue ball came out of Urn I over the sum of the probabilities, or the blue probabilities of all the Urns. Okay? Suppose I do the following, and say that we place equally spaced Urns on the segment 0, 1. Okay? So that's what happens. Let me tell you, let me kind of explain this graph. So here on the x-axis, we have the fraction of red balls for the unknown Urn. Okay, an unknown Urn is going to be chosen uniformly at random, and it will have a red fraction which is uniformly distributed between 0 and 1, since we uniformly distributed probabilities. And here on the y-axis, you have the expected number of votes for 3 different Urns. So the pure red Urn, that's the pure red Urn, so the Urn that has 100% red balls, the pure blue Urn, the Urn that has 100% blue balls, and the green Urn is just the unknown one, which changes as you change the x-axis. Okay, so what happens here? Well, suppose we end up picking the 20% red ball Urn. Well, you see that the number of votes the 20% Urn will take is strictly less that the number of votes that the blue Urn will, that the 100% blue Urn will take, which means the delta is actually negative, right? And since this happens basically for every point in the space, with the exception of 1/2 and 0, 0 really means that the unknown Urn is the blue one, and 1, which means that the unknown Urn is the red one. This means that with that probability, we'll end up losing over the first choice. So that's a very bad solution, even if it's the most natural one. On the other hand, the LP solution looks like the following. Again, this is the fraction of red balls in the unknown Urn. This is the number of votes. And here I'm plotting the whole red Urn, the whole blue one, then 25, 50, and 75%. And so you see that the green, the unknown Urn is always above every other Urn. You get the same number here, of course, because here the unknown Urn is equal to the 25% Urn. But you see that it's always above every other Urn. And that's, I guess, the closest I'm going to go in showing you what the solution looks like. Okay. So that's why ELP works. So again, if we use this Bayes approach for the linear program, we get a negative delta. The wrong Urn will get more votes than the right unknown Urn. So that's definitely a solution that we cannot apply, in the sense that if we were to apply it, we would lose with probability close to 1. And so one question that we were asked was, can we find positive solutions for which you win, for which delta is positive, that are easy to explain, right? And so I guess Bobby Kleinberg helped us in this, and so here is something that is relevant. So there's something called scoring rules, and they were introduced in the context of forecasting. And the general idea was the following: you had a TV station, or back then maybe a radio station, that wanted to guess what was tomorrow's chance of rain. So the station went to an expert, which knew, right, which is an expert and therefore knows what's the likelihood of rain tomorrow. And this guy knew it was really Z, but maybe he will lie and he will say X, right? So the TV station doesn't want this. It really wants to get the right probability. So what the TV station can do is say, well, so if it rains, if you claim X and it rains, then I'm going to pay you F0 of X, where F0 is a known function, so it's a public function. And if it doesn't rain, I'm going to pay you F1 of X. Again, F1 is a public function. So now the expert knows what's its expected gain, right? He knows that if he believes that, say, the rain probability is C, and he knows that if he claims X, then he will get an expectation Z times F0 of X plus 1 minus Z times F1 of X, right? The probability of rain times how much I'm going to get if I claim X and it rains, and the probability that it doesn't rain times how much I'm going to get if it doesn't rain and I claim X. Okay. And so this is a rich theory, but at a very basic level, what they show is that there exist couples of functions f0 and f1 over say 0, 1, such that for each z between 0 and 1, this function, the gain function of the expert, is uniquely maximized at x equals z. So the expert gets the largest amount of money if and only if he claims z as x. So he doesn't lie. Okay. So how can we use this in our case? And so the expert would say z. So let's do the following. Let's say that, and here I'm cheating and leaving out a lot of details, but that's really the art of the argument. If I pick a red ball, then I will vote for Urn I with probability Ri, and this Ri will be linear in F0 pi. And I won't tell you what linear means. It depends on how the pi's are distributed. But say you can think of proportional to F0 pi, even if this doesn't hold in general. And if I pick a blue ball, then I will vote for Urn I with probability Di, which is linear in F1 of pi. Okay, so that's what the voters will do. Again, it's a symmetric strategy. Now, that's the expected number of votes to Urn J if I is the unknown Urn, which is going to be pi times Rj plus 1 minus pi times pj, which you see looks quite a lot like gz of x, right? If we just use pi instead of z and pj instead of x. Right? Pj is actually F1 of Pj, so it really matches. And so the fact that GPI Pj is maximized at only at Pj equals Pi gives you that Bij is maximized only when j equals I. Okay? So this means that if you use the scoring rule induced solution, you get a positive delta, and therefore with enough many voters you will win the game. And that's, so the first solution we found to linear program was actually based on a scoring rule, and we didn't know that, so that's how Bobby helped us in identifying the scoring rule solution. And it's actually nicely looking. It's some sort of sum of quadratic functions over the PIs. So, I guess you can explain the solution that way. One issue, though, is that the number of voters needed scales as n over epsilon to the fourth. And this holds for best Italiani scoring rule we know of, and it holds as long as, say, the second derivative is, exists in 0, 1. So we need many more voters, and many more because, well, n over epsilon to the fourth is more than, or at least n cubed over epsilon squared, because epsilon is at most 1 over n. And the reason is you have the unit segment, you're placing some PIs there, and epsilon is just the minimum distance between two PIs, and therefore it will be upper bounded by 1 over n minus 1, right? So that's, so you can get a solution here which works, say, in the uniform case, where you distribute the red dots equally in 0 and 1, but in general it will be very suboptimal. And specifically, it will be very suboptimal in the important case where, say, you have only 2 or 3 or 4 Urns, so the original jury situation, guilty, first-degree murder, manslaughter. And in that case, n is a constant, so n cubed over epsilon squared is really epsilon squared, which is, again, tight with respect to the optimal centralized algorithm. An algorithm that gets to pick all the balls, see all the colors, and then decide. Right? Yeah. And I can, I guess you can say that the optimal LP solution is actually some sort of, optimal solution to a discrete scoring rule, or something like that. So if you define discrete scoring rule in some meaningful sense, in that, for instance, you don't get to vote for any x, and the state of the word is, a bunch of different possible probabilities, say a finite number, and you look at the minimum epsilon, then the LP solution is actually, it can be seen as an optimal solution to that problem. The one that kind of maximizes the amount of, the gap between the amount of money that the expert will get if he claims the truth. You actually see. Yeah. So that was it for the upper bound, for the strategy or the algorithm for voters. And I told you that the upper bound is tight in that you need this many voters if you want to win with probability at least 1 minus 0. Now, proving that was really, really hard. I mean, it's what took us most of the time. And it's kind of easier to get a lower bound for symmetric strategies. So the upper bound was, people were playing symmetrically. And, getting a lower bound for symmetric strategies is a bit simpler. But, the general lower bound, of course, holds even for asymmetric strategies, and so any set of algorithms. So I will only be telling you two ideas that we used in proving this lower bound. So first of all, observe that, suppose that voters are asymmetric, and suppose they tend to favor a few candidates, right? Suppose that, maybe we all do the following. We'll give a lot of weight to Urns from 0 to 2, and we give a very little weight to Urn n. Suppose we do this, right? So to, being more likely to get the right turn here, because we spend most of our votes in guessing which of these 3 Urns is the right one. Well, if we were to do that, then the adversary could really pick the Urn that we're kind of not caring about. In which case, of course, we will be wrong, because we're giving so little weight to the red Urn. And the other thing we show is that if voters are fair, in that they don't favor any given Urn, then the variance of total counts will be quite high. And the variance then gives you this kind of lower bound. And to show that the variance is high, we bound some properties, some second-degree properties of any feasible and fair strategy. So observe that from the LP, we got something that optimized, say the first moment, right? The linear property. So maximize the expected gap. But if you want to care about variance, then you need to take, the square, in which case the linear program doesn't really help you anymore. But we can prove that any solution, not just to the linear program, but to something more general, since people are doing different things, that second degree term will obey some law that will then allow you to show that the variance is high. And therefore, you will get this many voters. Okay, so that's the idea. Yeah. And so what I've been telling you about up until now is what's called plurality voting. So every voter picks a single candidate, votes for him, and then the single candidate that gets the largest amount of votes, if he exists, will be the winner of the election, right? But then, and you can claim this is the most natural type of election you can think of, but there are many others types of election. So for instance, that's something called cumulative voting, where where you as a voter can split your own single vote arbitrarily between candidates. So for instance, I'm the green guy. In plurality voting, I have to say, maybe I will be voting for B since it's my preferred candidate. But here I can say, maybe I will give 40% to A, 50% to B, and 10% to C. And maybe the yellow guy will make another choice. And of course, the weights don't have to be the same. Everybody can split his unit vote arbitrarily. So for instance, in this case, we can see that A gets a total of 0.8, whereas B and C get 0.6 each, which means that A will be the winner. So to find the winner here, you just sum the fractional amounts of votes he gets, and if it's the largest one, then he wins. That's how it works. That's called cumulative voting. So the very nice thing we found about cumulative voting is it's tight with respect to the optimal centralized algorithm. So N here disappears. So you can find a solution that requires only epsilon to the minus 2 log 1 over eta many voters, regardless of how many candidates you have. And moreover, the solution is really, again, the solution of that LP. So you basically have two possible votes. One, which is the solution of the LP if you pick the red ball, and the other one is the solution of the LP if you pick the blue ball. So you're actually, you can imagine that here, voters are really vote. When I say that they can split their vote, I'm saying that, they basically vote for a probability distribution, right? 40, 50, 10%. And so using those two probability distribution, you can get something as good as this. Then there's something, some other type of scheme, of voting scheme, which is called Condorcet voting. That's considered by many as the best voting system since it has a number of interesting properties. And here you don't have weights, but voters actually vote for permutations. So if I'm the green guy, I would say, well, I prefer A and then B and then C. And if I'm the yellow guy, I would say I prefer B and then C and then A. And how do you find the winner here? Well, you do the following. First of all, there's this concept of head-to-head election. So, maybe if you want to, given a set of votes, if you want to guess whether A or B is the best one, you just project every permutation on A and B, and you count how many times A is ahead of B. If this is more than a half, then A wins. If it's less than a half, then B wins. And if there's a candidate that beats every other candidate in a head-to-head election, then he is the winner of the Condorcet election. If there's no such guy, and in some cases it can happen, then you have to use some tie-breaking mechanism, and there are many of them. Yeah. So here, basically, there are no numbers involved. You just vote for a permutation. So we don't know what happens here, but we have a conjecture on distributions over permutations, and if the conjecture is true, then Condorcet voting is as good as the optimal centralized algorithm. So you need, again, 1 over epsilon squared many voters. So the conjecture is the following. There exists a probability distribution over the symmetric group, Sn, such that for each ij, I different from j, the probability that pi I is less than pi j is the minimum of 1 and 1 over pi plus pj. So, and if this is true, then with a couple of equations, you can show that 1 over epsilon squared many voters will be enough. Now, why do we believe this is true? So while we couldn't solve this problem, we could, I would say, we have an algorithm that actually produces, that we feel produces exactly these permutations. We just don't know how to analyze it. So we had originally a discrete algorithm whose solutions converged to this type of stuff. Then we, went to the limit. We took, we consider continuous functions, so continuous probability density functions. And we now have a function which, if it happens to be non-negative, and if it sums up to 1, then it's actually it's the probability density function of a random variable that gives you this. Okay, so, and to do this, so since here you see we have many numbers involved, right?
Yeah.
Pi and Pj is the rep probability of Urn I, and Pj is the rep probability of Urn j. And this has to hold not only for 2i and j's, that's easy, but so you have to find a probability distribution over the permutations for which, for each I and j, this holds. And so the hard part was really that you have these density functions, which are actually, which are multivariate functions. On the one hand, you have the pi, and on the other hand, you have x, which changes. So we basically, started from this, went back, trying to create a function that gave you this, and this requires solving an integral equation on 2 variables. And so now we have multivariate Taylor expansion of that function, and we feel that that Taylor expansion actually turns out to be a PDF, but we don't know. So all the details of these are in the paper. So to conclude, we have analyzed what we called information-based voting. This was introduced in the political science literature. The main point of information-based voting is you get a signal in one language and you want to map it to a vote in another language. You either saw the crime or not, and you have to choose which sheriff to vote for. And we have analyzed the efficiency of different voting systems in these different, in terms of information-based voting. So we have plurality, which requires roughly n cubed over epsilon squared many voters, n being the number of candidates. And plurality is optimal if n is a constant. So if the number of candidates is constant, then we have cumulative, which by using basically the same solution of plurality removes the n cubed term. The n cubed term was introduced because of this variancy term. And we show that cumulative voting is as good as the optimal centralized algorithm in determining which Urn is the unknown one. And finally, for Condorcet, we gave this conjecture plus a bunch of facts supporting it that you can find in the paper, which, if true, would give you that Condorcet is, again, as good as the optimal centralized algorithm. So 1 over epsilon squared many voters are enough. Then one thing that I've been assuming all along is that we only have 2 colors, blue and red. But in fact, you can imagine that you can have a richer set of signals. You could have, say, blue, yellow, green, red, and so on and so forth. So we've studied the multicolor generalization. Now you have probability distribution, not on just say, only on red and blue, but many, a lot of, say, C different signals. In which case we can prove that plurality requires some function of C times n cubed over epsilon squared. So if the number of colors is again constant, then it's tied. That function of C is something like C squared times log C, and we don't know whether it's tied. So that's an open question. Yeah, and I'm done. Thank you.
Do you know how much better are things when the players can communicate with each other?
Do we know that? Well, so if there's full information, so if everybody can tell, if people are not bounded, then of course the best you can do is 1 over epsilon squared. And on the other hand, if there's no communication, then you get n cubed over epsilon squared. Now, how this bound changes as you allow k bits of communication between people, I have no idea.
That metric you mentioned was the number of votes needed to get the right one with high probability?
Exactly. Yeah. Yeah. M is the number of voters.
Do you have anything meaningful to say about when fixing the number of voters that we have, how efficient are different systems at finding the right?
I see. Okay, so you mean, you give me a function of n and epsilon, which will be my n, and then I should tell you which is the best voting system. For some function, say 1 over epsilon squared, then yeah. In general, I have no idea. And in fact, we didn't really. So as I told you, the strategy we use is the optimal solution to the linear program. And it turns out that we can prove it's also the optimal solution to this problem, but we have no idea whether there exists a different strategy that has a slightly better constant or something like that. So it's actually a very hard problem, and I wouldn't know how to solve it.
But you said if you can pick the voting system that you want it from the optimal.
Oh, it's the optimal in terms if you disregard constants. In that you need 1 over epsilon squared many voters, but then maybe you need 10 over epsilon squared or something. I don't know about that. And in fact, no. So one thing that I've also been assuming is that, at least in the upper bound in the algorithm, is that voters are symmetric, right? I told you, voters are symmetric, and in general, even if you allow asymmetry, then you cannot really improve the bound. Maybe you can improve it by a constant, but not more than that. What we know is that there exist some inputs. So I can find you, say, even 2 Urns, such that if you allow asymmetry, then you can improve a lot the number of votes you need. Maybe you need only 1 over epsilon many voters, whereas in the worst case, then you still need 1 over epsilon squared. So asymmetry helps in some border cases, in some borderline cases, but in general, it doesn't help.
What if instead of an adversary, you have some prior distribution?
Right. Okay. So what happens there? So we didn't really try to basically solve all the details, but we believe that our lower bound proof works even if you choose the known Urn uniformly at random. But we didn't really try to check the details. And the reason is, what we show is that if you any Urn between, say, so the lower bound construction has Urns that are equally spaced between 1/2 minus epsilon n and 1/2 plus epsilon n. And their distance, of course, is maybe 2 epsilon and their n. And what we show is that so long as you pick between 1/4 and 3/4 of the Urns, so 1/2 minus epsilon, 1/2 plus epsilon, then you need at least this many voters. In that, if you have fewer voters, the variance will beat you. So my guess is it should work kind of directly, but we didn't try to prove it. Yeah, so the answer is the same. So that's my feeling. Of course, if that holds for uniform choices, but if you have a different strategy, so say if you tell me that, say, with high probability, you will choose 2 given Urns, then of course, it should be easier.